Okay, so lecture 9, 10, 27, 25. So last class, we talked about DFAs versus NFAs, right? So we saw DFAs were equivalent to NFAs, how you can convert any NFA to a DFA at some cost, but still in the same computational model, right? And that allowed us many interesting corollaries. For example, you can compute concatenation, clean star, still while being a DFA. And for NFAs, it also allowed us to show that you can compute negation of a language within the same model. Okay. And then we moved on to so these were all the closure properties that we were wondering about, and we got all of them in one shot. And then we defined a new quote unquote computation model of regex, regular expressions. Okay. And I stated a theorem at the end. We will regex versus DFAs/NFAs. Okay. And the motivation for regular expressions was that, okay, pattern matching is an important computational problem. Yeah. What's the regex term? Well, up to anything until lectures 1 through 8. Okay. Right. But, we didn't cover much in regex, right? And it's not there. We didn't do any exercises on them too. So apart from maybe a question about the definition, you shouldn't expect much, if at all. Okay. All right. And for today, the goal is to kind of understand, maybe do some examples of regular expressions and work towards proving Kleen's theorem, at least one direction. The other direction is more tricky, but we'll see how far we get. Okay? All right, let me also remind you of some important announcements. So first, homework 2 is due today at 9:59 p.m. on Gradescope. Okay, so make sure you submit them on time. Solutions will be released today at 10:30 p.m. Okay, so we'll post the solutions today at 10:30 so that you have time to review them for the midterm or first exam. And exam 1 is on Wednesday. Okay, so exam 1 will be here in class from 2 to 3:50 p.m. Okay, and just to answer the same question again, so material from lectures 1 through 8. Okay, mainly things that are covered in homework 1 and 2, maybe a little bit of the definition of regex, if anything, but nothing too complicated on them because we haven't done much, we haven't spent much time on them in lectures 1 through 8. And in terms of preparation, I would say homework 1, homework 2, there are a lot of, past exams available. Practice makes things much easier for material like this. Kind of understand the definitions. You don't have to memorize much, except for the theorem statements, if anything, right? There are one or two big statements that we saw. Just remember them, and no cheat sheets or no notes allowed. Okay. Any other questions about the exam, the logistics? Yeah. Yes, I will talk about that in a second. But any questions about the exam? Yeah.
What theory say we need to memorize them for like what?
I mean, memorize in the sense that, okay, let's say in the if you don't know that every NFA can be converted into a DFA, then some problem might become much harder, right? So that's what I mean. Or maybe the only numerical numbers that we really had was something like, okay, Shannon's theorem, 2 to the n over n. Okay, so remember Shannon's theorem, for example, or the other theorems that we had, to the extent that closure of, let's say, language clean star is also computable by DFA or something like that, right? Mainly the concepts, I would say. Okay. Any other questions? Okay. And after the exam, we will have a lecture 10 on Halloween. So you can dress up. I'll have some candy. I'll also dress up. So you have to be in class to see it. Okay. That will be in Kaplan Hall 169 with Andy / question. Okay. All right. And it'll also be recorded, and you'll also have access to it afterward. Any other questions? Yeah? Yeah, same time. Basically, the discussion sections are each Friday 2 to 3:50. And that's exactly the same time. And the other discussion sections won't be happening because I'm lecturing. So 169 is one of the discussion section rooms. So that's where we'll have the class. Okay. All right. So if there are no other questions, let me jump into the material. I mean, just for the exam, look at the past exam. They'll give you a very good idea about the kind of questions to expect and to think about. All right. And also do the practice problems on the homework. That will also help. Excuse me. All right. So last lecture, we were talking about okay, we were talking about regular expressions, and we motivated it from the concept of pattern matching problems, right? And there's a lot of history around it, obviously, which I'm not going to cover. For example, if you know scripting languages, something like Perl, how many of you have ever coded in Perl? I see one person. That's it. And there you see a lot of programming, which is almost like you're using regular expressions and nothing else, right? Something similar happens in like PHP and so on to a lesser extent, okay? And they are actually popular enough that they made it to XKCD, okay? So, okay, let's see. So this is something that maybe you do too. I do certainly, not in this bizarre way, but you search through 200 MB of emails. Imagine that. Now my email inbox is TV. Okay, so knowing regular expressions is indeed a superpower. Okay, so we saw some examples of utility. So for example, we looked at what we called, where was that? Sorry. So let me copy that again. Yes, let's do some examples before we dig into the main theorem. So we talked about this Fragile X syndrome where you're looking for this specific pattern, right? And it's a very important pattern or important problem to solve. And the scale is also kind of something that makes you think twice, right? Because the length of the sequence could be humongous. And the pattern description is small, but the length of the match can also be very, very long. Right? But we can encode this completely as a regular expression, right? So looking for the pattern, the regular expression that you're trying to match is basically GCG, CTG, and okay. So you can take the sequence of a person, and if that sequence matches this particular regular expression, then that's an indication that they might have Fragile X syndrome. Okay, we can encode this complete series of pattern matching questions as just whether or not a given sequence matches this particular regular expression. Okay, it's a very compact way of talking about all of these questions. All right, now let's do a few more examples. Okay. Let's say my language, this is something that we saw before, but let's anyway do it. All strings where the number of ones is divisible by 3. Okay. And let's say, the empty string is also part of this language, just by convention. 0 is divisible by 3, so why not? Can you give me a regular expression which can compute this particular language? Any suggestions? I need to match all things where the number of ones is divisible by 3. Any suggestions? Yeah?
That with 1 1 1 and then just plain star of that, repetition of 1 1.
Sorry, say that again.
You would have set where, or I guess it would be the main star of 1 1. So it would be repetition of 1 1. So it'll always be grades.
But you can have zeros in between, right?
Oh, I guess so.
But you're almost there.
You just put 1 1 0 or 0 1 1 0.
But that's I can have any number of zeros in between.
Have sorry.
So just modify what you said to put any number of zeros in between. Yeah? Can you be a little bit louder? I can have any number of zeros, right? Does that capture something like, let's say, not quite, right? Yeah? Exactly. Right. So the final suggestion is I can put something like this. Right. So actually, maybe I should, let's say, idea 1, 1 1 1 star. The problem is there are no zeros. I can put 1 0 2 0, but I can actually have any number of zeros in between, right? So let's just fix that. And I can also have any number of zeros in the beginning. There may be redundancies. That's fine. Okay, we're not trying to write down the most compact regular expression. We're just trying to write down one regular expression, right? And then a big star also. Does it make sense? So I'm saying if the number of ones is divisible by 3, any such string can be matched to this. Okay. Any questions? No, fine. All right. So let's do one more. Let's do a couple more. Say L is our favorite other language. All strings where the fourth bit from the end is a 1. Now I want to capture all strings where the fourth bit from the end is a 1 as a regular expression. How can I do that? Initializations. This was trickier with DFS. It was relatively easy with NFS using epsilon transitions or with zeros and ones. But now we have to do it in using regex. Yeah?
Could you do like 0 star, 1 star, and 1 non?
Well, I guess ... is not our regex language. It's allowed in some other things, but let's say basically do 0, 1. Almost works, except these things need not be a string of zeros followed by a string of ones, right? I can also have 0, 1, 1, 0, or anything in any other pattern. Yeah?
0, 1 star.
Exactly, right? So okay. So essentially, how are we coming up with these things? Well, you need to think a little bit like what the problem is asking. What do these strings look like? The fourth bit from the end is a 1, right? So I'm encoding the fourth bit explicitly here. Okay, this is the fourth bit from the end. And the other 3 bits can be 0 or 1, right? So 0 or 1, 0 or 1, 0 or 1. And what can come before that? Anything. We have no control on that. So 0, 1 star. Okay, any questions about this? No? All right. Okay, maybe let's do one more example. Let's say L equals all strings all strings that contain 101 or 010 in them. Any suggestions how I might capture this using a regular expression? Yeah.
Do like the 0 or 1 star and then 101 or 010 and then 01, like 0 or 1 star again.
Mm-hmm, that would work. Okay, because you're just saying, okay, somewhere in the string, I need to have a 010 or a 101. What comes before and what comes after, I don't care, right? This 01 star is basically our way of saying, I don't care what's appearing here. I only care about what comes later. Okay, you can play around with these things. Okay, we can go over the examples that we did earlier. Like, for example, what if I want them to be alternating? What if they want my language to have the first and last strings be the same, and so on? Okay, and this is just to give some intuition for regular expressions. All right. Okay, so now let's get back to the key theorem or key construction that we're aiming for, and we'll see some really important algorithmic consequences for this. Okay, by definition, regular expressions look so different from DFS, NFS, and everything else, but it turns out that they are equivalent. Okay, And in fact, the way we will show the first part is to show that for any regular expression, there is an NFA which actually computes it. Okay, that's what we'll show. We won't show it directly at DFA. We'll show an NFA, and then we can use our powerful theorem that every NFA has an equivalent DFA. Okay? So what we'll actually show is that given any regex R, we can build an NFA for R, meaning we can build a NFA N such that for every string X matches R if and only if N of X equals 1. Okay, we're only showing one direction. The other direction is a bit more involved, but I think this is a more interesting direction. Okay. Any questions about the statement? The statement is clear? Okay, so before going into the proof, I want to say a little bit more about what we'll show. We'll show this theorem, but we won't pay too much attention to how efficient we are in constructing this NFA. Okay, you can construct some NFA, but you can actually be super efficient in constructing it, and you will do that in the homework. But I want to emphasize that for the following reason. Okay. Let's say more detailed version. Given any regex R that has quote unquote size M. Okay. Think of size as basically, how many characters you have in writing your regular expression, or more conceptually as number of compound operations or number of characters. No. Okay. I mean, these are equivalent up to constant factors. So whichever makes it easier to think about, just use that. Okay. So for example, if I have 0/1, then how many compound operations is it? I have the base string 0. Well, I guess I want to include even the base things as the ingredients. Okay. So it's, let's say M equals 3. Because I have 3 operations more or less. I have 0, 1, and then the OR. Okay. But all of these will be constants, and it's not important how you exactly count. I can even count parentheses, then it'll become 5, but 3 or 5, the constant won't change. Okay. Something like, let's say 0, 1 star, then again, M is like 3. I have one concatenation operation between them and like a star, and then the base operations, so things like this. Okay. Oh, maybe it should be 4. 4, yeah. Right? Or just think of it as the number of characters. Count parentheses, don't count parentheses, just stick to one convention. Okay. But the beautiful thing is when you build the NFA, okay, the number of states your NFA will have is just a constant times the length of the regular expression. Again, it's not like I'm blowing up the regular expression humongously. You gave me regular expression of size 10, my NFA might have 20 states in it, but no more. Okay, does the statement make sense? I'm saying I can actually write down an NFA which can do the matching for you, and the number of states is not much higher. Okay, and we can actually even show something more, which is exploited critically in grep, is that and the number of non-dead state transitions is O of M. Okay. Not only does the NFA have only like O of M states, the number of arrows is also very small. It's a very compact representation. Okay. We will show the first one in the lecture. The blue part you'll show in a homework. Yeah.
We're still zero.
Still 0, 1 for this. Otherwise, it'll scale with the alphabet size. Or you can just include, actually, it doesn't scale with the alphabet size. I should take that back. It just means that your transitions will have arrows which correspond to the alphabet size. Does that make sense? So the number of states won't grow, but the number of arrows will grow just because the alphabet size is bigger. Okay. All right. Now, what is a practically important consequence of this? Last lecture, we saw that if you give me the transition table for an NFA, then I can write Python code for it, which runs pretty efficiently, right? So we can go back to, where is that? Week 4. Yeah, run NFA. Okay, give me any NFA. The amount I can write Python code for it, which runs in time n times the number of states. Okay. So if you put Kleen's theorem together, especially with this more detailed version together, what do we get? Corollary. Given a string x of length n and a regex R of size m, we can check if x matches R in time, which is O of n times m. Okay, why? Well, first, use Kleen's theorem to construct a NFA for R. Okay. And then use run NFA on X to check if X matches. Okay. So we can check pattern match for regular expressions very fast, n times m. Why do I say very fast? Remember, we talked about, so just as, to give us, place O of n, m in context. Okay. So we started out this whole story by saying, okay, can I solve a simple pattern matching problem? I give you a string x of length n, a pattern p, of length m, and we wanted to check, okay, does this particular pattern occur somewhere? Right? And there was a simple sliding window algorithm. Check the first m bits. If they match, I'm done. Check the next m bits. If they match, I'm done, and so on. Okay? That simple algorithm took exactly this much time. But now for the same cost, we are able to match any regular expression. Forget exact string matching. We are able to do any regular expression matching basically in the same time. Right? That is very remarkable, I would say. Okay? And this is the algorithm that's used in grep. Right? So, with optimizations, of course, this is what grep or generalized regular expression processing. Okay, and this was developed by Ken Thompson, one of the co-inventors of the language C, and another Turing Award winner. Okay. And it uses these two steps, basically. Construct a NFA for the regex, and two, simulate the NFA. Okay, so every time you're running a grep search or using search and find using the star characters, internally, you're doing something like this. Right? Any questions about this? No, yes. Okay. In fact, you can do something even better for some contexts. Okay. What do you mean even better? Sometimes, like think of Fragile X syndrome, right? The pattern that you're matching is not changing, but the input changes a lot more. Make sense? Right? So the pattern that you're trying to match is always the same. I have to scan 100,000 people to check, okay, who is more susceptible to this particular syndrome, right? But the pattern is not changing. It's always the same. Where did it go? This GCG, CGG, AGG star CTG. Okay, fixed length pattern, right? The input length, on the other hand, the X is in the millions or even hundreds of millions, right? Can I do anything better in that context? So let's say, every person who comes into my hospital, I want to check if, they and whose genetic sequence I have, I want to check if it matches this particular pattern. Can I do something potentially better? Any guesses? Yeah? Maybe, but we probably don't know where the pattern is going to be. Right? In fact, the pattern can be very, very long. That's kind of the magic behind this O of n times algorithm, right? The final match, even if the pattern itself is very small, what you end up matching can be very, very long, right? CG, this middle portion, CGG and AGG, that can be repeated 100,000 times. What else can I do? In a cases where M, the length of the pattern, is significantly smaller than the length of the string that I'm searching over X. Any sessions? Think of the other theorem that we talked about, which was to convert every NFA to a DFA. Okay, so for example, right? So let's say n equals 10 to the 10. And m is maybe 10. Right? Now, O of n times m is roughly 10 to the 10 times 10, which is 10 to the 11. A factor of 10 blow up. Okay. The other thing I can do, which would be better in some cases, is the following. First, construct a NFA for the regex. The number of states is O of M. Okay. If I'm matching the same thing again and again, it's probably worth it for me to spend the additional pre-processing time and just convert this NFA to a DFA once and for all. Okay. So I can then convert the NFA, let's say N, to a DFA D. The number of states is now 2 to the M, 2 to the O of M. So let's say we ignore the constants. Depending on how you count, you can even make it something like this. So 2 to the M. Okay. So now I have a DFA instead of a non-deterministic machine. I have a deterministic machine with more states. But what's the potential win here? Why would you do this? Why would this be a win from an algorithmic standpoint? Any guesses? Well, if we go back to our simulation algorithms, what was the time complexity of run DFA versus run NFA? Yeah. Exactly, right? So it's going to be additive versus multiplicative. So, and then you use run DFA D to check on D to check if X matches R. Okay. So what does this mean? I can check if X matches a regex R, okay? In time, it's a length N, size M. In time, either N times M by the first approach, build an NFA, run the simulation algorithm, or I can do it in something like N plus 2 to the N. Right? Yeah? It's an excellent question. It turns out that you can actually do this in O of M time as well. In fact, as we'll see in the proof itself, it'll become clear that it is basically O of M time. It's linear time. Okay. So you can do either of these two things, either N times M or N plus 2 to the M. Right? So for something like Fragile X syndrome now, so this would have been like 10 to the 10 times 10. And this is like 10 to the 10 plus 2 to the 10. Right? So the second one would be much faster, especially if if you can store the DFA and just run the same DFA for people again and again and again, it's going to be much, much faster. Okay. Any questions about these two complexities? All right, so this is just to give you an idea of how we can use NFS and DFS to really do fast pattern matching for regex. Right? Okay. So let's now go back to the powerhouse behind these two complexities, right? Now, how are we getting such fast algorithms for matching regular expressions? Well, we have to prove Kleen's theorem. Okay, so let's do that. So what is our goal? We are given a regular expression R, and our goal is to build an equivalent NFA N for R. Okay. So the basic idea is to kind of follow the definition of the regular expressions and just show that each step can be captured by a NFA. All right? Well, if you want to do that, how did we even define regular expressions? We had base case, no, actually, let me. Okay, we have the base cases. Let's see, or let's show that these can be captured by NFAs. That's not too difficult to believe. I mean, these are very simple languages or strings, right? And then we'll show how we can capture the compounding operations using NFAs again. Okay, but that's the work that we've already done, so we get to reuse it. Does it make sense? So the regular expressions themselves were defined using induction, like iteratively, and we're going to use the definition in how we're going to build the NFA. Okay. So for instance, let's say I want to do this guy. I want an NFA which only accepts 0 and rejects everything else. How do I do that? I'll get you started by drawing the start state. Okay. Yeah. Exactly. Just one arrow, which is a 0, and all the missing arrows are going to dead state. Okay. And if you ask me for a 1, I can do something similar. Okay. It only matches the string 1 and nothing else. How about the epsilon? I want an NFA which only accepts the empty string and nothing else. Yeah. Actually, you don't need any transitions, right? So I can even be even more simplistic and just this. Okay. And lastly, let's say I want to do the null pattern. Well, for this is even simpler. I can just do this. No except states. Okay. For all of these base cases, I basically have an NFA with two states, 1 and 1. Okay. Now, in the definition of regular expressions, we had compound operations. We had 3 compound operations. First was concatenation. The next one was OR. And the last one was clean star. Okay. So these are the three ingredients or three rules which allowed us to make more and more complicated regular expressions starting from simple. Okay. So our approach for building the NFA is also going to follow the same kind of path, which is imagine I give you an NFA for R1, NFA for R2. How do I construct an NFA for the new one that you build out of this regular expression? Okay. But we kind of saw that already, right? This one we know how to do. Concatenation is easy with NFAs, right? So if we have a NFA for R1, and let's say NFA N1 for R1 and NFA N2 for R2, we can build one for R1, R2. Okay, because this is basically like concatenating the two languages, right? So let's say this is the start state for one. This is NFA one N1. It has all kinds of arrows. Ooh, this is confusing. So let me draw it maybe a little bit better. Okay, if you had something like this, and maybe NFA N2 is something similar. What can I do now? We know how to concatenate NFAs, right? So as we discussed, we can just add epsilon transitions. And then, okay. Any questions? All right. That's for the first compounding operation. For the next one, if we have a NFA N1 for R1, NFA N2 for R2, then how do we do the OR of the two NFAs? Let me just copy them. How can we do it? Yeah.
Start fitting.
Yep. Okay. Clean star, same thing. We know how to do it already, right? So if we have I'm repeating the same thing again, but since it's the nth time I'm doing it, let me do this a little faster. We can build a NFA N star for R star using this was N. We would create a new dummy start node, epsilon. Okay, that's it. Yeah, question?
Can I ask you about like true?
Mm-hmm.
I kind of I'm still kind of confused on like why it took O of M n to run the NFA, but it took like O of n plus two, and to run the.
Oh, so this n plus 2 to the m, the 2 to the m is to build the DFA. After that, it's O of n.
So I'm kind of confused about why it takes O of n to run it on DFA as opposed to O of n times n.
Oh, okay. So that's a good question. So we can go back a little bit. And where is that guy? It should be right around here. Right. Okay. So this was our code for simulating a DFA. Right. So we just read a bit, take a jump, and go. So that's why each time you enter the loop, you're only spending a constant amount of time. Right. Whereas for an NFA, we had to do the union of sets. Okay. And in fact, as stated, it's even worse. It can take m squared time. But if you use fast union operation, then you can make it O of m, because the number of things I have to take a union over is potentially every possible state. Okay. So you are entering the loop the same number of times, but the cost of each iteration is now higher. Because I have to, like, let's say I have 10 states that I have to branch over. I have to compute them and take the union of them. Does it make sense? So here, each one of these is like one lookup, and the number of states I can have is m. So I might be doing at least m lookups. In fact, I have to do m unions, but the cost will at least be m, or the number of states.
Okay, so the transition function can be constant time.
Yeah,
Looking up
the table is constant time.
but we might have to look at the table.
Multiple times, exactly. Right. Yeah. So in standard, like, when you think of arrays, we say looking up an entry is constant time. That's the model that we are using. Okay. Right. And this n plus 2 to the m comes because I need to build this DFA first. And after building the DFA, is just like a single pass, which is very cool. All right. Okay. So that's how, we can now, if we do these operations again and again, we can build a NFA for any regex R using the above 3 steps. Okay, and hence prove Kleen's theorem. Okay, what's really remarkable, historically, at least in my mind, I didn't know about this until much later, is that Kleen actually did all of this without ever defining NFAs, or without the advantage of somebody defining NFAs for him. Okay, but if you look at the paper, there's implicitly a notion of NFAs and so on in the paper. And this predates Dana Scott and Rabin's definition, but I think he didn't identify the importance of non-determinism, whereas the other paper really pinpointed, okay, non-determinism as a concept can be very powerful. Okay, let's just do a simple example so we get our bearings right. And I'll do a very simple example because this conversion, when done manually, can be tedious. But as I said, every time you're doing grep, you are doing this conversion. So how can we do this? Well, we'll first break up this as concatenation of two regular expressions. There are many ways to break it up, but this is kind of at least seems simple enough. I need a DFA, NFA, which only accepts 0. Okay, which is my, maybe let me say it properly. This is R1. This is R2. Okay. So I'm going to write down something which only accepts 0. All right. Now I need a machine which computes 10001 star. How do I do that? I'm going to further break this up, right? So this is basically, I need something which computes 01 and then take the clean star of that, right? So how can I do 10001? I'm going to do, this is the start, 1 0 3 0, right? And okay, actually, let me do it properly. So I need to do 100. Let me build a NFA which only accepts 100, and that's easy because I can do something like this. Okay, and let me do an NFA which only accepts 01. Right? Now I can put the two together to compute something which only accepts 100/01. The OR, how? Create a new dummy start node, split between them with epsilon. Okay. Now, how can I do clean star of that? We know how. We have to just follow the things mechanically. I'm going to create a new start node, 0 double prime, and then add, oops, this should have been an accept, and epsilon edges to here. Okay. And finally, to get the concatenation, I would just do, let's say, one more epsilon. Okay. So by following this process, I've constructed a NFA which exactly matches equivalent to 0 versus 10001 star. Okay. The final one might not be the cleanest, but it's fine because we're doing it kind of in a mechanical way, but just following the same steps again and again. All right. Any questions about the process? No, yes. All right. Okay. The magic, as I said, really is that you can do everything very efficiently and you can get very fast algorithms for matching stuff. Okay. And the other cool thing is just as for NFAs, if someone asks you, okay, find me a string, write down a regular expression which checks if a string does not match a regular expression. That's quite complicated. Okay. Like, for example, I say, okay, give me a regular expression which checks if a string X does not contain 101 or 0. That's quite complicated. But nevertheless, we can do it because we can convert to DFS, use that not needs easy for DFS. Okay. All right. And there's no shortcut here. If someone says, okay, give me all things in my library which do not match this particular regular expression, it's quite involved. You have to convert it to a DFA, do a negation of that, and then match it. All right. Okay. So that's basically it for regular expressions. The main thing is that it's an alternate way of looking at NFAs, DFAs. Turns out to be an alternate way, even if it was developed kind of separately with a very practical purpose in mind. All right. So let's take a 5-minute break. And when we come back, we'll kind of do a quick review of what we've learned and then move on to the next topic. Okay. So the last 4 lectures or so, what did we cover? We more or less covered 3, well, let me use a lighter color. We covered 3 computational models: DFAs, NFAs, and regex. Right? All 3 had the important property that the description of the machine was independent of the input, meaning they can process things which are much, much bigger than their description. Okay, unbounded, right? And for us, luckily or very interestingly, all 3 are equivalent. Okay. And in general, you'll see this in other places. We say a function is regular if it is computable by a DFA or a NFA or a regex. Okay. And we also studied various closure properties of these things. And it wasn't just a curiosity. The closure properties led us to interesting questions and also to kind of the final algorithms for regex, which are implemented everywhere. Right? Okay. And you can take maybe 2 sort of perspectives on this. One is, let's say, programmer's perspective of DFAs or NFAs. Right? So our first simple model that is not size limited. Okay. And also, they are really useful for string matching and more generally for pattern matching problems. Pattern matching, processing, any such operations, DFS and NFS are very, very useful. Right? So this is stuff that we've already covered. And there's kind of like the next step up that you can do, which is like state space coding and so on. Okay, this is stuff that shows up a lot in control theory, in robotics, and so on, where you're coding things based on states. You're in a certain state, you have to take some action. The concepts of DFS and NFS are definitely at play there. Okay. Of course, the input is a lot more fuzzy. There's a lot of probabilities involved, but you're just building on the base case. Base case are DFS and NFS. Okay. The other thing is they're also related to single pass memory bounded algorithms. Okay, also called streaming algorithms. So these are called streaming algorithms because you imagine someone streaming the input past you. You see one bit at a time, and you don't have enough memory to even store even much information about the input string. Okay. For example, if you're an IP router, you're really running a streaming algorithm. No matter how much memory you have, the number of packets that you're going to see is much, much, much higher. Okay. All right, that's from a programmer's perspective. Obviously, these two are overlapping, but the other perspective, why they are so kind of insight, they give us very good insights, is as a theoretician, a very simple model. The same thing again, very simple model that can handle unbounded lengths. Okay, the first point is the same. It's both important practically and also from like theory perspective. And the other thing is, studying automata led us to this powerful concept of non-determinism in computation. Okay. And also, hopefully I've convinced you that intermediate abstractions are very powerful and helpful, right? You could potentially have come up with the whole algorithm for grep without knowing NFAs, but that would have been a Herculean task. Whereas if you had the concept of NFAs, DFAs, it's almost like an extension of the theory that were already built in the context of NFAs. Okay. And such thing happens a lot in theory. You build intermediate models, and then you kind of completely get rid of them for the end algorithms, but use the intermediate models to develop the algorithms. Okay. All right. So that's kind of my spiel about DFS and NFS and why they're nice. Now let me tell you what's not so nice about them. Okay. So the first question that we should have in mind is, okay, they're very good at computing all kinds of things, but can they actually compute everything? All right. So the next few lectures, we will study some limitations of DFAs. It turns out they do have some limitations. And then we'll see how to overcome. Okay. All right. So as an example, let's think of the following function. So far, we've been very successful, right? I told you a function, asked you to design a DFA, NFA, or regex, you've been able to do it. But now let's say I gave you the following function. Okay, majority of X just checks whether there are as many ones as zeros or there are less ones than zeros, right? Again, a simple function, majority of 0, 1, 1 is 1, majority of 0, 1, 0, 1 is 1, majority of 0, 0, 1 is 0. Again, let's say the empty string, it's 0, it's 1 as well. Okay. Now, if I ask you, okay, give me a DFA for majority, what do you think? Is it computable by a DFA or not? No, yes. No? Okay, how many of you think you can compute majority by a DFA, NFA, or a regular expression? Nobody? All right, you guys are very pessimistic. Okay. The answer is surprise. It should be surprising that the answer is no. Okay. right? So it turns out actually that majority you cannot compute using DFA, right? Okay, now I told you the answer is no. We'll see why much more concretely later. But what's the intuition? Why do you think majority is much harder to compute by a DFA than something else? They could easily do many other things, right? We said, okay, I can check if the number of ones is divisible by 3, but why can't I check if the number of ones is more than the number of zeros? Yeah.
No. Sorry.
Almost, right? But on the other hand, if I ask you, okay, tell me whether the number of ones is 0 mod is divisible by 3, even then the same objection might have arisen, right? So what distinguishes between these two things?
The number of.
Right. So you need to know it exactly, yeah? Right. So intuitively, it almost seems like majority is impossible to compute. Because we have to count the number of ones, right? So the objections that you mentioned boil down to this. Somehow it seems like if I don't know the exact count, how will I know? Right? And if I want to know the exact count, I need to store that number, but the number can grow with the input, whereas the number of states cannot grow. If I only have 10 states, I just cannot store more than 2 to the 10 numbers, right? Indeed, majority is not regular. Okay, remember regular meant that it is computable by a DFA, NFA, or regex equivalent. Okay, so there is no DFA that computes it, right? And let me give you another language now. X contains an equal number of zeros and ones. All right. So alternately, if I say EQ, I can talk about a function which is EQ of X, equals 1 if number of zeros equals number of ones and zeros. Okay. So for instance, EQ of 0, 1, 0, 1 is 1. EQ of 0, 1, 1 is 0, and so on. Okay. How many of you think EQ is not regular? Can I see more hands being raised? And indeed, EQ is not regular. Okay. And we'll again study it formally. But what's the intuition? Yeah. That's true. But also, like, again, the same fundamental bottleneck seems to be there, right? That how can I do this if I don't know how to count? Right? So EQ is not regular as we cannot count using DFX. I'm putting cannot count deliberately because it's a, It's just a conceptual idea at this point. We haven't made it concrete in any way. Okay. All right, let me now define another example. Now, this is the last one. I'll stop boring you with these examples and we'll jump into stuff pretty soon. It's, let's say EEQ. One, if X contains an equal number of 0 ones and 1 zeros. Okay. I can ask, okay, earlier I was counting, is the number of ones equal to the number of zeros? Now I'm asking, okay, is the number of 0 ones the same as the number of 1 zeros? Okay. And how many of you think, the same intuition almost seems to be true, right? You really need to count. Okay. Just as before, how many of you think EEQ is not regular? See several people raising their hands now, but that was a trick question. Okay. That was entrapment. EEQ is actually regular. Okay. It's very similar to EQ in how we conceive of it, right? Seems like, okay, even for this, you need to count, right? I need to count how many 0 ones are there, how many 1 zeros are there, and then compare the two. And it seems like there's no other shortcut, just as for zeros, ones, and also for majority. But strangely, this EEQ function is regular. Okay. Why is that? Why is this EEQ special, even though it looks like it is counting, right? It really is like counting. I have to check, are the two things exactly the same? But it turns out this is easier. Any guesses why? Yeah?
In order to have another 0, 1, you have to have a 1, 0. So the difference between 0, 1 to 0 is about.
Exactly. So you can work out some test cases. The idea is that, if I have a string of zeros, it doesn't change my count at all, right? And if I have a 1, then I'm going to increase 0, 1. If there's a 0 afterward, then I'll get a 1, 0, and so on, right? And you can play around with this a little bit, but basically EQ of X equals 1 if and only if the first and last bit of X are the same. Fascinating, right? We saw this language already in the first, when we defined DFAs, we looked at this language. Can I check if the first and last bit are the same? Yes, there was a DFA that we drew for it. But if I ask you in a different way, is the number of 1, 0 the same as 0 ones? It seems not regular, but it's the same language. Okay. And the reason is, you had to do some case analysis and verify it. But basically, if I have 0, 1, 0, 1, every one followed by 0 gives me a count for 1, 0. And if there's a switch, I get 0, 1. And if I have a string of zeros, none of this makes any difference. Okay, until I see the 1 again, the counts don't change. Okay. So for instance, here, the number of 0 ones is, let's see, this guy, this guy, this guy. It's 3. Whereas the number of 1 zeros is this, 2. Okay. Now the first and last bit are matching. The number of 0 ones is the same. 3. Number of 1 zeros is 3. Okay. So our intuition that, okay, because we have to count something is not regular is false. So the fact that majority is not regular is something special about majority. Okay. And, you can make the same question for different patterns. Like, for example, let's say, I'm kind of feeling in a bad mood. So I'm going to ask you, X has an equal number of 0 zeros and 1 ones. Is this language regular? Or let's say this is EQQ. Okay. It turns out that EQQ is not regular. Okay. And a couple of years ago, when I was teaching this class, after this lecture, one of the students came to me and said, have you heard of ICPC? Have you ever taken part in that? ICPC is, I forget what the acronym stands for, but it's basically a programming contest for college undergraduates, right? UCL has a team, every college has a team, and then they have finals always in very exotic places. I think in Cairo once, last it was somewhere in Kazakhstan or some place like that, right? It's a very fun competition. And one of the problems there was this. You are given strings P, Q as input. Okay. And let me write it properly. So input is this, and this is an ICPC problem. You're not going to solve it, but I just want to state the question because I think it's very cool. Is the language EQPQ 1, or is the function X has an equal number of P's and Q's, 0 else regular? Okay. So like, for instance, if I gave you 0, 1 and 1, 0, the answer is yes. If the pattern was 0 and 1, the answer is no. The pattern was 0, 0 and 1, 1, the answer is no. But now they're asking, okay, what if I gave you something like 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1? You have to tell me if this counting problem is regular. Okay. And you can solve this by giving a nice algorithm for it. I'll let you think about that. But, and if you want to know more, I can tell you, okay, in office hours. Okay. But in general, this just the intuition that, okay, because I seem like it is, because it seems necessary to count, doesn't mean that's the only way to solve the problem. There may be a much cleverer way somehow. Oh, why can't I match each 0 to a 1? Every time I see a 0, I should wait for a 1. Why doesn't that work for majority? Why can't I play around with that and get a DFA for it? Okay. Fortunately, there are very concrete things we can show. There are very concrete ways to show limitations of DFAs. Okay. Is there a question? So we have, DFS and NFS are one of the few computational models where we know everything. Okay. As we'll see, when we throw a little bit of a twist on that, things go haywire. But at least for DFS and NFS, we understand them very, very well. Okay. In particular, there are two tools. One called pumping lemma. I don't like the name, but that's what's been around historically. And other one, which is Mihl-Nerode theorem. Okay. So the first one can show that a language is not regular. Okay. And the second one can show, again, similar to pumping lemma, can be used to show a language is not regular. In general, showing something cannot be computed is much harder than showing something can be computed. Again, as a general statement, not always true, but as a general statement. Like even for circuits, showing Shannon's theorem's proofs was more involved than showing that there is a circuit for every function. Okay. And one reason is, okay, I ask you to prove something is regular. Okay, give me a DFA and you're done, right? Whereas if you want to show that there is no DFA for it, you have to rule out every possible DFA. Okay? So you need some abstract property or something which separates things computable by DFS from the specific function or language that you're studying. Okay. So both of these can do that. Depending, we'll spend more time on pumping lemma, and we'll spend a little bit of time on Mihl-Nerode theorem. I didn't do this in previous years, but we are a little bit ahead, so I think we have enough time to include a little bit of Mihl-Nerode theorem. Both can be used to show a language is not regular, but Mihl-Nerode theorem goes a step further. Okay, it exactly characterizes the best possible DFA for any language. Okay, can tell you what's the best possible DFA for a language, if one exists. All right. So Mihl-Nerode theorem, or MNT, is complete. If a language is regular, it'll tell you what's the best possible DFA for it. If it's not regular, it's a complete characterization. So it'll prove that for you. Pumping lemma only goes one way. If you can use it to prove something is not regular, you're fine. But there are languages which are not regular, but you can only prove that they're not regular using Mihl-Nerode theorem. Okay. So my plan is to cover pumping lemma and kind of the easy direction of Mihl-Nerode theorem, and then we won't do the harder direction. I will state the result nevertheless. Okay. All right. So what's the pumping lemma? And as I said, to prove something is not computable is usually harder. Okay. And the way we do it, like we did in homework 1, when we said and or is not universal, right? We had to find a function and show that no circuit which involves only ands and ors can compute. So there we identified a property of things that you can compute in this model and showed that the function that you're studying does not have this property. Okay. In the same way, we're going to identify a property that every regular language has and show that majority does not have this property. Okay. It's kind of a general attribute that every regular language must satisfy. There's no way to avoid it, but our majority does not have this property. Hence, majority is not regular. Okay? That's the general idea. And what is this magical property? It's a mouthful, all right? So a lot of quantifiers, we'll go over them again a little bit more carefully by examples. But let me first state it. Okay. Suppose I give you a function, f is from 0, 1 star to 0, 1. Again, whether functions or languages, it's the same. You can work with either formulation. For every such function, if it is regular, there exists a number p. Okay, there exists a special number p. Such that any string x where f of x equals 1 and the length of x is greater than or equal to p has a special property. Okay, what is that property? Let me draw a picture. Saying for every language, if it is regular, there is some number p, like 10,000, you write that number down. Any string which is bigger than that has the following property. Any string, remember, it's any string. I can break up this string into 3 pieces, A, B, and C. Okay? Okay, I can break it up into 3 pieces such that the following conditions hold. 1, well, let's say we can write x equals ABC, where okay, this is the most important property. It's saying any string which is bigger than this number p can be split into 3 pieces where you get to pump, that's why it's called pumping lemma. You get to repeat the middle piece any number of times you want. Okay? It places a big constraint on your language, right? It's saying f of ABC equals 1. This implies that f of AC equals 1. F of ABBC equals 1. F of ABBBC equals 1, and so on. Okay. Just the fact that the first one is in the string, in the evaluates, the function evaluates to 1 on the first string, forces you to also evaluate to 1 all of these other things. Okay. And the next condition, without which the first one would be meaningless, of course, is length of B is not 0. Meaning B is not empty. Duh. If it's empty, you didn't do anything, so you didn't gain anything. So that's something that you need. And the third piece is strictly not needed, but is helpful in some proofs. Length of AB is at most P. Okay. So all we're doing here is saying any regular language must have this property. Okay. And then we will use this to show certain languages are not regular by basically showing that majority cannot have this property. Okay, this property pumpability or pumping lemma separates regular languages from some other languages. Okay, does the statement make sense? Any questions? Give me any string bigger than whatever number p, like 1,000,000 you write down. Once you write down the number, you lose control. I can give you any string which is bigger than that. There must be a way to split it up into 3 pieces where you get to repeat the middle piece how many ever times you want. Yeah? Yeah, exactly. B star. It's basically like saying somehow you need to have a regular expression embedded inside every possible x, which is bigger than this length. Okay? Yeah? No. In fact, A and C could be empty too. You know, really, like B is not empty, is the only piece that we have. Okay? Yeah?
But it has to be, like, is B or B and B the same thing?
Yeah, both are the same. You mean this P and this P? Yeah, these are the same. Yes, I'm splitting the string into 3 pieces. The middle piece is not empty. You get to repeat it how many ever times you want. Okay. There was a question somewhere else here, or yeah? So that's why we had to prove this, right? But it's saying this is a property that every regular language has to satisfy. It's a hard constraint. In fact, that's why majority cannot be regular. Okay. It's a property of or limitation of DFAs, really. Okay. And often when we're showing limitations of computational models, this is how you do it. You identify a property that everything that is computable in this model satisfies, and then kind of separate it from something else. Okay, that's kind of the only, one of the few approaches that we have. Yeah. We will use it to prove something is not true. Oh, but it's not complete. So it's necessary but not sufficient. Okay, that's a very good question. So this is only necessary for regular. There are languages which satisfy these conditions but are not regular. That's why MLT is more powerful. That's like if and only characterization, but it's a little bit more involved to apply. So we'll do both. Okay. Any other questions? Okay. So, the statement of this is a mouthful, but when we try and use it, hopefully it'll become clearer. And we will talk about this and MNT on Friday. Okay. And remember, you'll have exam here in class on Wednesday. And the TS will be here to proctor the exam. I won't be here, but good luck with the exam. Practice all the previous exams. That will help you a long way. Okay. All right.